Hi everyone, my name is Fabricio Fernandez and I will present the work landslide occurrences in China during Wenchuan earthquake. Earthquake, mainly with strong ground motion, can trigger thousands of landslides in mountainous regions. Landslide disasters is one of the most destructive geohazards. Simulating these phenomena requires advanced numerical techniques. In this work, the massive Daguanbao landslide occurred during the Wenchuan earthquake is modeled in 3D using the material point method. Focus is on the simulation of the failure mechanism and the runout process of the failed mass. The 3D model was developed considering spatial variation of the materials into the domain. The constitutive modeling of the material includes elastoplastic models with linear strain softening and tensile strength cutoff. The numerical results in 3D are compared with previous results in 2D and with the reported topography post-earthquake. This presentation is organized as follows. First, the landslides triggered by the earthquake are described. Then the Daguanbao landslide in geomorphological and topographic context are described. The following describes the material point method, its formulation and its numerical implementation. In relation to the numerical models, the discretization process, the constitutive models, and the initial boundary condition are detailed. Finally, the results and final consideration are shown. The magnitude 8 Wenchuan earthquake occurred along the Longmen-Shan fault system. It was the result of motion on a shrinking reverse fault along the margin of the Sichuan basin. The earthquake occurred along a 240 km rupture zone with a maximum estimated slip of 9 to 12 meters. The Wenchuan earthquake triggered a large number of landslides, with a distribution that was higher in density along the thrusting segment of the fault than that the strike slip segment. The Daguanbao was a massive landslide of an estimated volume of 750 million cubic meters. The failed mass involved in the rupture moved approximately 4.5 kilometers, blocking the Guangdongxi Valley and forming a nearly 600 meters high dam. Figure number 1 shows the digital elevation model before the earthquake. Figure number 2 shows the topography after the event. In these figures, we can identify the Daguanbao Mount and the Guangdongxi Valley. The geological map of the region shows the presence of 5 geological groups distributed in the event area with different mechanical characteristics. In this figure, we can identify the landslide characteristic section AB, the final topography delimitation, the source area and the accumulation area of the Daguanbao landslide. This figure shows the post-earthquake characteristic section defined by the segment AB on geological map and allows us to identify 2 important characteristics of this event. The first one is the formation of a near vertical wall near the Daguanbao Mount, and the other is the formation of a dam over the Guangdongxi Valley. Before building the computational model, we can identify some relevant characteristics of this event from the point of view of numerical simulation. It is a large-scale problem which may be associated with high computational costs. The failed mass presents very large deformations, which may be associated with mesh issues like mesh distortion. It is a dynamic process. Under the action of the earthquake, the material have non-linear constitutive behavior and the model presents heterogeneities within the domain, which can generate possible discretization inconvenience. In this work, we use the material point method that has a specific characteristic that I will describe in details. The MPM is a hybrid Lagrangian-Eulerian numerical method suitable for solve large deformation problems. In this method, Lagrangian particles can move freely within a fixed Eulerian mesh where the differential equations are solved. The figure below shows a computational cycle in the MPM context. In number 1, all properties stored in the particles are interpolated to the nodes. In number 2, the equation of motion is solved at the nodes of the computational mesh. In number 3, the nodal solution is interpolated back to the particle, and then number 4, the position and velocity of the particle are updated. It is noted that the computational mesh isn't distorted during the computational cycle. In the NPM, the motion equation in differential form is solved at the nodes of the Eulerian mesh through its discrete form, where the nodal values are calculated from the Lagrangian particles using interpolation functions. In this equation, P is the nodal momentum, and the right part of the equation is the total nodal force, formed by the nodal internal force and the nodal external force. In the NPM, the interpolation functions are needed to transfer information between particles and nodes. In the GIMP, the interpolation functions are the integral of the product of the particle's characteristic function and the nodal shape function over the particle domain. This particle's characteristic function allows to approximate any material property by its particle value. In 3D, the interpolation function is the product of its value in each direction using the relative position of the particle regarding the nodes. In this figure, we can see the definition of the particle characteristic function and the nodal shape function used in this work. The particle characteristic function takes 1 inside the particle domain and 0 outside. The nodal shape function are the conventional two-node linear shape function. After performing the integration, the interpolation or within function are defined. In figure number 2, we can see this function is non-linear and extends beyond the finite element domain. Once the nodal acceleration had been calculated, namely the motion equation was solved at the nodes, the position and velocity of each particle can be updated. Then the strain increment in each particle can be calculated using the nodal velocity gradient. The particle stress increment is determined from the strain increment using a constitutive model. In order to consider a rotation in large deformation problem, in this work the Geomechanics stress rate is adopted, where the omega is the spin or vorticity tensor. The NPM formulation previously presented here was computationally implemented in the NPM Pack Rio code. This numerical implementation can be summarized in the following steps. First, we can identify two types of operation at the nodes and operation on the material point. First, mass and total forces are calculated at the nodes. After that, the motion equation is solved at the nodes. After imposing the boundary condition, this solution is interpolated back to the particles, where velocity, position, strain and stress are updated. After that, all nodal values are cleared and another cycle can start again. The numerical discretization of the Dagwan-Bao landslide requires the adequate representation of a large-scale 3D zone with variable heterogeneities inside the model. The main challenges associated with the discretization are the creation of a quality 3D mesh using only the raster data, namely the digital elevation model, and the inclusion of these spatial heterogeneities inside the 3D mesh. In this work, the methodology used to build the discrete NPM model of the Dagwan-Bao landslide is based on the work of Fernandez, and it has the following characteristic. It's based only on the raster data, on the land, and on each material. Finite element meshes are not required during the process. The 3D model is created only from the elevation data of the land. The heterogeneities are included using the elevation data of each material. The complete sequence to construct the NPM discrete model is summarized in the following step that will be described in detail in the next slide. Number 1. Obtain the digital elevation model of the land and the digital elevation model of each material. For each point P, establish the material elevations over that point. Number 4. Establish the NPM discretization, namely the cell dimension and the number of particles per cell. After that, establish the base material as current material and construct a model from bottom to top. If any particle elevation is greater than any material elevation, then switch the current material to that material. In figure number 1, in A we can see the digital elevation model of the land, and in B and C the digital elevation model of each material. In figure number 2 we can see the NPM discrete numerical model consisting of 2 million particles. In 2A the elevation of the particles in meters, and in 2B the material distribution inside the model. Figure 1 in A shows the failure zone identification where areas of intact material are observed. This identification was used to delimit the elastoplastic behavior of the materials in the numerical model. Figure number 2 shows the initial characteristic section before and after the rupture zone delimitation. The numerical model includes 3 different materials: an elastic material representing the base of the model, and 2 elastoplastic material. The peak resistant parameters of material 2 and 3 used in this model are those reported by He et al., where the author estimated the parameter from laboratory tests. For material 2, softening parameters are used to calibrate the model with the observed topography. The numerical simulation has 2 stages: an initial stage where the elastic behavior of material is assumed and the base of the model is fixed in 3 directions. In this stage, vertical displacements are allowed in the vertical plane as boundaries. The second stage is the failure one, where the materials involved in the failure are assumed to be elastoplastic, and earthquake is applied at the base of the model. In this stage, no reflecting boundary conditions are applied of the side of the model. It is important to note that failure surface is not imposed on the model. This figure shows the failure evolution in section AB in terms of effective plastic strain in the 2D model. It is observed an initial plastification zone near the contact with the bedrock. After the earthquake releases its maximum energy, this initial zone extends to the foot of the slope, from which the failed mass slides and collapses. In the final configuration, the valley is completely covered, forming a dam, and the formation of an almost vertical wall is also observed. In this animation, we will see the failure evolution and the run-out process in the 2D model. It is important to note that the failure surface wasn't imposed in the numerical model. This figure shows the failure evolution in section AB in terms of effective plastic strain in the 3D model. It is noted the formation of an initial plastification zone near the contact with the bedrock that is higher than that presented in the 2D model. It is noted too the formation of near vertical plastification zone forming or suggesting the formation of block inside the mass. It is noted too the explicit separation of the materials at the top of the model forming a vertical wall. The numerical model suggests blocks traveling around 1000 meters during the run-out process. This figure shows the comparison of the final topography of the characteristic section AB. The 2D results obtained by Fernandez correctly captured the formation of an almost vertical wall and the formation of a dam over the valley. Other 2D results also captured the formation of a dam over the valley, but the vertical wall was less reproduced. The results of this study in 3D correctly captured the formation of a vertical wall, the formation of a dam over the valley, and as well the formation of blocks inside the mass. Figure number 1 shows the comparison of the failure surface obtained with the NPM models in 2D and 3D. We can observe a good agreement between the results in terms of failure surface. Figure number 2 shows the comparison of the final topography of the model. The 2D model correctly captures the height of the material above the valley and the vertical wall formation, but it overestimates the topography in the middle of the model near the coordinate 3000. The 3D model captures the vertical wall and the topography in the middle of the model, but underestimates the material deposited over the valley. In this work, the massive Daguanbao landslide was numerically modeled in 3D using the material point method. The numerical results in 3D were compared with previous results in 2D and with the reported data. The failure surfaces suggested by the 3D and 2D model were consistent with the reported failure mechanism. Within the failed mass, the 3D model captured near vertical damage zones may be associated with block formation during the runout. The 2D model adequately captured the formation of a vertical wall without the need to limit the failed mass region. The 3D model requires this delimitation to capture the vertical wall formation. This may be associated with the fact that the parameters of the material were assumed to be constant in space. In our opinion, a higher resolution of the variation of this parameter is still necessary. And thank you very much for your attention.